So I study black holes in the universe, and I study black holes around galaxies that are inside the galaxies. And one of the major things that has come up in the last, say, 10 to 15 years is that there is a very significant correlation between the mass of the black hole and the mass of the galaxy. What I'm ultimately trying to understand, what we are ultimately trying to understand, is how a galaxy forms, how it evolves, how it acquires mass, how the stars form inside the galaxy. And because of this correlation that we have found between the mass of the black hole and the mass of the galaxy, this means something very important for how the black hole may affect the galaxy itself. And this is a new realization, and there's been lots of theoretical models in trying to explain this. So for example, we know that when you have a black hole sitting in the middle of a galaxy, material will fall into it, and that naturally happens because as a cloud of gas moves around the galaxy, it can collide with another cloud of gas that will cause it to fall down towards the middle of the galaxy. The black hole is sitting there, and this material tries to fall into the black hole, and then it can't all make it into the black hole because the black hole has such a small component. It's so small that the material tries to squeeze down in, and then it blows out. And as that material blows out, it affects the galaxy itself. And so in effect, there's this relationship, but it's a relationship that is built up because as you try to dump material into the black hole, it comes back out and affects the material that it falls into. And so therefore, there's this, what we call a feedback mechanism between how much mass you can put into the black hole and how much a gas mass there is in the galaxy. And since it's the gas mass that determines the stars in the galaxy, then you get a regulation process between the mass of the black hole and the amount of stars you can make in a galaxy. So this was a relatively new understanding. We always thought the black hole, had been there, but we never thought it had any special role in terms of the evolution of the galaxy itself, mainly because it's a very small component of the total mass of the galaxy. The black holes that we have found are, of average, about 0.1 to 0.2% of the total mass of the galaxy. So the surprising result is that something so small in terms of the mass of the galaxy can have such a significant effect on the galaxy itself. And the main result is, and the main reason is because the black hole is in a special location in the middle of the galaxy, and it is so small that as you put material into it, there is an incredible amount of energy that is generated just because of the gravitational energy that can push back out onto the galaxy itself. So these black holes in the middle of the galaxies, their mass ranges from about 1 million times the mass of the sun up to 10 billion times the mass of the sun. The most massive black hole actually was found on the Hubble-Eberly telescope out at McDonald Observatory, and that was 20 billion times the mass of the sun. It's just it's an incredible monster. It's in a very weird system. It's in a system where the black hole is about 15% of the total mass of the galaxy. So it's of order 100 times more massive compared to the galaxy mass compared to all the other galaxies that are out there. So it's a complete oddball out there. And one of the things we do as scientists is we love to study the oddballs because that's where you learn so much about the physics. You want the general trend, but then when you look at the extreme cases, so either at the extreme upper mass end or at the extreme lower mass end, and when we're talking about black holes, for example, that's when you really learn a lot about the physics. And especially at the upper mass end, because at the upper mass end, the black hole has the most. If a black hole is very massive, it has the most amount of energy it can produce, because the amount of energy it produces is basically coming from the mass of the black hole itself, the gravitational potential of the black hole. So if the process if the physical process is related to this feedback mechanism, then you learn the most by looking at the most massive black hole, because you can see that feedback almost in a direct sense. So that's one aspect. You study the most massive ones, but we also study the least massive ones. And in fact, there is a lot of effort out there to try to find a galaxy that has no black hole. That has not happened yet. There have been some galaxies that are pure disk galaxies. When we talk about this correlation of black hole, it's normally a galaxy that has some type of bulge, some type of roundish spheroidal component. And when we look at galaxies that have no bulge, it's kind of a hit and miss as to whether it has a black hole or not. So we believe that the black hole is related to this, whatever is making the bulge component of the galaxy. And so we are really working hard to try to find that galaxy that has no black hole, the sun. So there's been a big campaign to try to measure black holes and globular clusters, and it's been very controversial. I mean, I myself has been involved in a lot of controversy. I did my thesis on black holes and globular clusters, and when I did my thesis, I said no. The next year, I wrote a paper where I said maybe. 2 years later, I said yes. And about 2 years after that, there were about 3 papers that said I was wrong. And so it's just been going back and forth, back and forth. And now we have, I would say, 3 to 4 globular clusters where the evidence is fairly strong. There's one where it's extremely strong. So this is a globular cluster in our nearby galaxy Andromeda. It's one of them. It's one of the largest globular clusters in our local group. And that has the strongest evidence by far. But what's special about that one is that we think that globular cluster is not a globular cluster. It's in fact the nucleus of a galaxy that fell into this big galaxy, and the outer part got stripped away, and you're left with this nucleus. So if all galaxies have a black hole, if you strip the outer edge and you have something that looks like a globular cluster, you still have a low mass black hole, but it's not necessarily a black hole in a bona fide globular cluster. So we've been trying to push to objects that we think are bona fide globular clusters, and the evidence again is just on the edge. You know, it's like this what we tend to use in astronomy is this statistical number. About 5 sigma is a significant 5 sigma significance is what we use in astronomy. That would imply you have about a 99.99% probability that it's real, and which is pretty, you know, that's pretty impressive. So you'll be amazed in astronomy how many times 0.01% actually it turns out to be real. That's kind of something about statistics there. And so these handful of black holes are about that significance. So we're not running to the press yet, but this is a very active ongoing effort to try to measure black holes and globular clusters. Again, the key here is you're pushing to the lower mass n, and that's when you learn the most again about these about the correlations.